Look at a modern mega airport terminal. From the outside, it looks like a static monument of glass and steel, a giant waiting room where millions of people stand in line. But that stillness is just an illusion. Inside, an airport operates as a highly engineered, relentlessly active machine. It breathes in thousands of people, baggage, and aircraft, channeling them through a continuous, high-speed flow. From the exact second you step through the automatic doors, a vast hidden network of sensors, algorithms, and cameras wakes up. It begins tracking your position and managing your path before you even locate your flight on the departure board. Aircraft delays and heavy storms are routine problems. The true threat to this megastructure is the sheer unpredictability of human crowd surges. A sudden influx of thousands of passengers can easily jam systems designed for a steady stream, yet the system rarely breaks. The engineering triumph of an airport lies in how it absorbs that daily, overwhelming chaos and translates it into a quiet, seamless stroll to your boarding gate. This invisible management starts right at the terminal entrance. Smart surveillance cameras constantly scan the floor, running computer vision software that calculates the exact density of the crowd in real time. If a sudden bottleneck begins forming near a security gate or a check-in desk, the algorithm detects the clustering bodies. It calculates the failure point and proactively dispatches ground staff to reroute the crowd before the line actually collapses. Once at the desk, your boarding pass is the primary link. Encoded in ink is your flight, destination, and baggage data. Generating it triggers an immediate reaction. Local databases, airline servers, and global systems synchronize your status in milliseconds. Before your physical body even turns toward the security line, your digital twin has already navigated the airport's global data network, reserving your space on an aircraft sitting thousands of miles away. While you walk upstairs, your luggage drops beneath the floorboards into a hidden, multi-kilometer network of high-speed conveyor belts. Every bag hits a CT scanner, which bombards the suitcase with radiation. Dense metals block it, while lightweight plastics let it pass. Imaging software strips away low-density shapes, leaving operators with high-contrast rotating 3D wireframes to quickly spot hidden objects. Cleared bags move instantly to the sorting phase. RFID scanners read the tag on your suitcase, feeding the flight number into the central routing algorithm to calculate its exact destination track. If your flight is minutes away, software identifies your late bag, triggering mechanical diverter arms to forcefully swat it onto a high-speed express lane. You might be casually drinking a coffee by the departure gate, entirely unaware that 30 feet beneath you, your suitcase is running a violent algorithmic race against time. Back upstairs, the lack of massive lines is a result of queuing theory. Algorithms mathematically predict peak traffic hours based on historical flight schedules, opening exactly enough counters to prevent the floor from jamming. Even the sound you hear is carefully engineered. If thousands of voices and rolling luggage echoed off hard surfaces, the noise would become overwhelming. Instead, acoustic engineers formulate the ceiling panels and wall textures with specific porous materials designed to trap those sound waves. The atmosphere itself is actively managed. Hidden sensors continuously measure ambient carbon dioxide and human body heat in the terminal. As a massive crowd gathers, giant HVAC chillers automatically flush the zone with fresh, cooled air. These systems work together to neutralize the physical stressors of the terminal, ensuring the environment remains comfortable even as the density of the crowd increases. All of these micro-adjustments flow into a single hidden room, the Operations Control Center. Here, live data feeds allow controllers to make split-second decisions, dynamically shifting flight gates the moment a crowd bottleneck starts to form. Keeping this digital command center, the miles of baggage belts, and the massive chillers running requires the electrical consumption of a small city. Redundant power grids and heavy backup generators sit on standby, ready to activate in seconds. In a highly secure, closed-loop system, a blackout is an immediate security threat. The airport survives the daily pressure because a localized failure, a blown circuit, a jammed belt, or a crashed server instantly triggers a pre-planned mechanical contingency. Every element operates in total simultaneity. The algorithms map the queues, the chillers balance the air, and the global servers sync the databases, all at the exact same moment. It requires massive, heavy industrial mechanics to bridge the gap between those invisible digital systems and the physical reality of a 70-ton aircraft. Heavy storms will hit the runways, delays will stack up, and massive crowds will surge, but the infrastructure absorbs the shock. The next time you walk toward your gate, look at the walls around you. This is a massive, precision-engineered machine, where every movement is calibrated by science and software. Have you ever looked up as a plane comes in for a landing and wondered why another flight doesn't suddenly appear on the same runway? From the ground, the sky looks completely wide open, but up there, you're dealing with thousands of passengers, highly unpredictable weather patterns, and millions of pounds of heavy machinery moving at hundreds of miles per hour. An airport's operations actually begin kilometers away in the sky, within a tightly monitored control zone run by air traffic control. The second a plane enters the zone, its altitude, speed, and heading are tracked every single second. To keep this movement fluid, controllers must solve a three-dimensional puzzle of fuel levels, wind speed, and spacing for every flight simultaneously. Mid-air traffic is organized into specific air routes. Think of them as invisible aerial highways that pilots navigate using GPS and ground-based radio beacons to stay strictly in their designated lanes. When a runway is congested, air traffic control redirects planes into a holding pattern. This precise, racetrack-shaped waiting loop suspended in the sky forces the crew to recalculate fuel weight, burning thousands of dollars in jet fuel. Hanging in the air is an active, high-stakes calculation balancing atmospheric conditions against the aggressive realities of fuel burn. Once a plane is cleared to leave the holding pattern, it enters the approach sequence. Controllers rapidly issue commands to drop altitude, turn to specific headings, and reduce airspeed. The goal is to perfectly align the aircraft with the runway centerline. If the plane comes in too fast, too high, or at the wrong angle, touching down safely becomes physically impossible. To lock in perfect alignment, airports use the instrument landing system. It broadcasts two radio beams, verifying horizontal center and vertical descent angle. Even if dense fog drops visibility to zero, the ILS crosshairs precisely guide the aircraft right to the asphalt. During a blind descent, pilots aren't relying on their eyes. They are quite literally writing a mathematical radio beam down to the ground. The exact moment of touchdown initiates a violent sequence of physics. A 300-ton machine hits the asphalt at roughly 250 kilometers per hour. The runway itself is engineered to help absorb this impact. Beneath the surface, advanced drainage and friction systems prevent hydroplaning, keeping tires gripped tightly to the road, even in a torrential downpour. To stop that massive forward momentum, the plane relies on a synchronized mechanical sequence. Panels on the wings, called spoilers, flip up, instantly killing aerodynamic lift. Almost simultaneously, the engines engage reverse thrust, redirecting massive exhaust flow forward as an aggressive atmospheric brake. Landing an airliner is a highly coordinated mechanical assault against massive forward momentum. Once the plane is safely down, the external control system shifts its focus to a new set of unpredictable variables. Weather dictates everything here. A sudden shift in crosswinds or a localized storm cell can force controllers to instantly cancel incoming landings. And then, of course, there is biology. Airborne bird strikes pose a severe mechanical threat to modern jet engines. To keep the airspace clear, airports deploy a mix of organic and technological countermeasures. This ranges from dedicated radar tracking and high-decibel sound cannons to deploying trained predator birds to hunt and scatter local wildlife. Managing the daily operations of an airport means actively fighting both biology and atmospheric physics. Flight delays are often simply the result of this ongoing battle against nature, rather than an airline error. Navigating to the terminal requires ground movement control. With dozens of planes rolling along taxiways at any given time, surface radars map out every movement to prevent collisions in the tight spaces between gates. At the gate, a totally unseen operational turnaround begins. Ground crews offload high-value cargo, while massive underground pipelines pump jet fuel into the wings, requiring strict grounding cables to prevent static electricity sparks. Looking ahead, modern airports are deploying AI-powered digital twins. These are exact virtual replicas of the airport, used to simulate traffic, predict weather impacts, and solve surface congestion long before a bottleneck actually happens. This network of mathematics, radar, and human oversight functions as the real foundation of global travel. While piloting an aircraft is the visible part of the journey, the ongoing coordination of hundreds of flights every hour requires a system as complex as the aircraft themselves.